I spent 200 hours engineering a leg for my robot dog, because fuck getting a job. It's made out of carbon fiber, so it's super lightweight. It's got 3 degrees of freedom, which makes it possible to move in X, Y and Z axis. And the thing I like most about this leg is the servo hub. All motors are placed inside this single part which barely moves, that way most of the mass is stationary and the leg can move really fast. This video is gonna be all about the engineering. I'm gonna derive the inverse kinematics, go through the code, explain how the leg moves and why my dog is scared of it. But like all good things in life, we are gonna start with the Fusion 360 assembly. I just finished modeling, hopefully the final version of this leg. Basically took the latest design, made it smaller, remodeled a bunch of parts, and because of parametric modeling, it took me only a single day to model. In Fusion you get these things called parameters. These parameters allow you to basically set variable dimensions, so instead of using a set dimensions for the diameter of these tubes, I used a diameter of D, and I can change expression for D anytime I want. I'm gonna change it to 8mm, which is what the new design uses, and you can see it got pretty fucked up. This is the case almost always with parametric modeling. You actually have to go back in this timeline and change all the fucked up features. But it still speeds up the process and you don't have to change every single diameter manually. You can just update the expression and it updates the whole design at once. So now I'm going to assemble it and let's hope it's rigid enough. I started off by cutting up some carbon fiber tubes. And I'm using some water, that's just because I don't want to breathe in the carbon fiber dust, which is harmful. After that I got to the main assembly, and as I said before, the main idea behind this new design is taking the latest design and making it smaller, lighter, but keeping the rigidity, which is quite a challenge. I did this mainly by decreasing the diameter of the tubes, and that's not because of the tubes. The tubes actually weigh next to nothing, I think it's 20 grams for the whole leg. The reason I decrease the diameter is so that I can make all the 3D printed parts smaller, which are the majority of the weight. As for the joints, each revolve joints consist of an M3 bolt and a spacer. The spacer has a diameter of 3.1mm, which is close to the 3mm diameter of the bolts, so there's very little backlash, and since it's made out of metal, the joints should last a decent amount of time. The M3 spacers are just press fitted into the 3D printed parts, but I had to use a hammer for most of the fits. For the material, I'm printing everything from PLA Pro. It's better than regular PLA because it's got a higher impact strength, higher tensile strength, and in my experience it's a bit more ductile, so it doesn't crack as easily. I got this filament from my sponsor Instalogic. They actually do lab tests for their filaments, so you can get the parameters like the tensile strength, shore hardness and stuff like that. Otherwise they do engineering grade filaments, so if you want TPU90A or carbon fiber infused filament, I'm gonna link them in the description and you can check them out. The leg was strong enough to hold up its own weight, so I decided I'm gonna add some payload to account for the weight of the robot. I was doing some calculations to decide which payload this leg needs to withstand. So this leg weighs 260 grams. I plan on adding a third motor, so if I just add 50%, the leg should weigh 400 grams. Then for the body of the robot, I assume that the printed parts, the tubes, it's gonna weigh about 200 grams. The battery is 250. I might add some buck converters, which are 70 grams each. So the total weight of the body is gonna be 500 grams. 4 legs plus the body, the robot should weigh 2.1 kg. Since the robot is going to walk such that 2 legs are touching the ground at the same time, if I divide the body weight by 2, I get the weight per leg, which is about 1 kilogram. But it already weighs 260, so I just need this leg to lift 750 grams. To increase the payload of the leg, I got 2 main options. I can shorten the carbon fiber tubes, but this would make the robot smaller. So I decided to go with the second option first, which is adding a spring to offset the weight of the robot. If you're wondering why I added 2 springs in series instead of just 1 spring, when you try to compress the spring, you can't really do it. But if you got 2 springs in series, they just collapse like this. The leg can jump, which is good. This is 500 grams. Oh wow. Before this leg could lift 300 grams, now it's able to lift 500. So these 2 springs added 200 grams to the payload. If you like building robots, you should check out my sponsor PCBWay. With PCBs, you can take all of these wires, components and compress them into a single circuit board, just like this one I used for my hexapod. In my next video, I will actually be getting a PCB for this robot dog, and PCBWay makes this process easy. You just choose the board dimensions, number of layers and color, like this purple one you can get for free this September. Then you upload your Gerbil files and track the manufacturing process in real time. You can also choose their PCB assembly services, which is what I planned to do because soldering sucks. So thank you PCBWay for allowing me to make these projects. I can't wait to see this robot run. At this point I decided that the 2 degree of freedom leg is finished, so I just did some final touches to make sure every part is decent and I don't have to remake it 4 times once I build the whole robot. Now I'm at the point where I think the design is decent. There is no obvious way to make significant improvements. I think I can finally go ahead and add the 3rd degree of freedom. To add the 3rd servo motor, I printed this elegant part. It's a servo hub that houses 2 servo motors just like before, and the 3rd motor is actually gonna be attached perpendicular to them. The whole servo hub needs to rotate, so I used a spacer with an M3 bolt again. I even got to use this tool, which I never use. So this is just a screw. It gets screwed in through this part and it sticks out into a spacer that's inside this part. Oh yeah, this looks super cool. If you're wondering how I made these parts look like they're made out of carbon fiber, I actually got this plate, Bamboo Lab carbon fiber. I typed that into AliExpress and it makes this nice pattern. So I was just mounting these servo motors and noticed a potential issue. Right now the bolts aren't tightened all the way and you can see that the servo can flop around a lot, and that's because of these bolts. So I decided I'm gonna use bolts with a countersunk head. This should help the servo to self-center. And now it's perfectly aligned. By the way, these gaps between the servo motors are for passive air cooling since the motors get hot. So I just printed, hopefully, the final version of the servo hub, and as I'm disassembling the leg, I can finally feel the spring force without the gearbox of this servo slowing it down. It's pretty cool. Alright, now I want to show you the cable management I came up with because I think it's pretty sick. So as you can see, the servo hub went through many iterations. At first I had no cable management, then I added this hook for servo 2, then I added it for servo 1 as well, and then I changed the design to like these buttons, and now it finally works. So you just press the cable in like this, and then you twist it into place. And now all the cables come straight up. Again, now I want to actually make this thing move, so for that I need to solve inverse kinematics. So I'm gonna do that on paper and then transfer it to code. There's 2 main ways to control this leg. You can either control the joint angles, this is called forward kinematics. That way the foot moves in an arc, or you can control the foot position. So you choose the XYZ position and the leg will move there. With inverse kinematics you can do cool stuff like making the foot move in a straight line, but this comes at a cost. You need to solve a shit ton of equations. Firstly, I'm gonna consider the leg to be just these 2 links. The kinematics of this leg are more complicated, but we're gonna build up to that. So these are the 2 links of the leg. Here is the foot and here is the base. We know the foot position because that's the input, and our goal is gonna be calculating theta 2 and theta 3 out of this position. We can draw this triangle, and this is gonna help us calculate these angles. L23 is just gonna be the square root of these coordinates squared. It's also going to be helpful to know the angle, so I'm going to call this angle gamma 3, and that's just going to be the arctangent of x over z. To get theta 3 we kind of need this angle, so I'm going to call that alpha 23, and to calculate it we're going to use cosine law. Now we can solve for alpha 23, and theta 3 is just going to be 180 degrees minus alpha 23, but I'm just going to write that as pi. This is just 180 degrees in radians. So we solved the first motor angle, and now we need to solve theta 2. To get that, it would be useful to get this little angle. I'm gonna call it alpha 2, and we can use cosine law again to calculate it. Then theta 2 is just gonna be gamma 3 minus alpha 2. So these are the kinematic equations for this simplified version of the leg. Now we're going to move to the 3D case. The leg is going to rotate around the x-axis, so we're going to look at it from this side. That way x is just going to be pointing straight up, y is going to be pointing to the left, and z is going to be down. From this side, the leg is just going to be a straight line. Going to look something like this. Again, we know the foot position, and we want to calculate this angle. Because of the coordinate system, if you point your right thumb along x, these angles are positive, so this angle is going to be negative. So this is going to be minus theta 1. And to calculate it, we can just take the arctangent of y over z. So minus theta 1 is arctangent of y over z. Therefore, theta 1 is going to give us minus that. Now we need to make a correction. So before we assumed that this is a 2D case, but if you took this mechanism and rotated it around the x-axis, you need to make the z coordinate longer to account for the rotation. Therefore, we need to change the z input for these equations. I'm going to call it z2d, and it's just going to be z divided by the cosine of theta 1. So instead of using this length, we're going to feed this length to these equations for the 2D case. These equations are still not accurate because in my mechanism, the x-axis is actually translated both in y and z-axis. So the x-axis is about here and the whole mechanism rotates around this point. Until now, we assumed that this mechanism just rotates around this axis, but in reality, the pivot point is actually here, so the axis is moved in both y and z coordinates. Before, this 2D case was just a straight line, and now this straight line is here, so this is the 2D mechanism. It's not rotating around this axis anymore, it's rotating around here. Therefore, we got ry and rz. This angle is now minus theta 1. We know ry and rz because that's just how we modeled the robot. We know the foot position y and z, and we want to calculate this angle theta 1. I'm going to call this r1 and I'm going to call this r23. We can easily calculate r1 because it's just going to be the Pythagoras for these points. We can also calculate r1 differently. We can, instead of y and z, we can use r23, rz and ry. So I'm going to do that. And this is also equal to r1 squared. From this equation, we can get r23. Now we know all the lengths of this triangle and we can start calculating angles. So I'm going to call this angle beta 1. And that's just going to be the arctangent of y over z. Then we can get this angle. I'm going to call it beta 2. To get beta 2, we can just use the cosine function. Since we know beta 1 and beta 2, we can get theta 1. So minus theta 1 is going to be beta 1 plus beta 2 minus these 90 degrees. Again, going to write that in radians. Theta 1 is going to be this. And now we need to make another correction. So instead of this simplified case where the axes align, now this length is r23. So for these equations, instead of using z, we're going to use r23. And this way, the full inverse kinematics are solved for this case. Now we're going to go through the code and implement these inverse kinematics equations. So L2 and L3, that's just the link length. The link length is always from the point of rotation to another joint, which in this case is actually this one. And then we go again from the point of rotation to the center of the foot or to the end of the linkage. So L2 is 160 and L3 is 153. And that's what I've put in the code. These two lengths are the result of moving the x-axis. So this is the actual pivot point. And this is the pivot point we assumed in our equations. It's just going to go through the center of this tube and through the axis of rotation of theta 2. We get that rz is 21 millimeters and ry is 48 millimeters. And that's exactly what's in the code. These are just the equations we derived for the 3D case. Then we change the coordinate system. So instead of using z, we're going to use r23. Then we just use the 2D equations. Here we need to make a change because of the linkage we are using. So when I move this servo motor, you can see that only theta 3 changes, which is good. But when I move this motor, both theta 2 and theta 3 change at the same time, and this is a problem because that's not how we derive the equations. So whenever we move theta 2, we need to move theta 3 by the same angle, and that's why there's this plus in the equation. And in the end we just change the units from radians to degrees. And the last thing is to sort out the servo offsets. So instead of using the angles calculated from Inverse Kinematics, to set the actual angles of the motors, we need to offset them. When the servo motor is at 0 degrees in the code, in reality it's actually at the middle angle. That's just so that it can rotate both to the left and to the right. And then there's offset from the geometry. Even though these two servo motors are at 0 degrees, this third link is at an angle of 22 degrees. And we need to subtract it from the offset. So I created this move function. Firstly, we used this inverse kinematic function to calculate the angles. Then we add the servo angle offsets, and then we write the servo angles. And this write to 70 function, that's just this piece of code. If you have 180 degree servo motors, you can use the default function. And then you can use it in the code. You just select the servo motors, select the coordinates you want the leg to move to, and update the angle variables. So solving the inverse kinematics, doing all of these corrections, writing the code, it might seem like a lot of work, and it is if you do it for the first time, but once you understand it, it's not actually that bad. Yeah, if this goes right, I'm gonna be shocked. Holy shit. Yeah, it fucking works. Let's go. I did all of this first try. My high school math teacher would be proud. So as you can see, now if I want the y-axis to be 0, it's not here, because the pivot point is actually here at this bolt. So that's why the leg is tilted when the y position is set to 0. If you want to support me or just build this leg, I'm gonna put the project files on my Patreon. I'm not sure if I'm gonna use this coordinate system for the robot dog. Only a component of the force is being used to lift the robot up, so I might actually use the configuration where the leg is just pointed straight down. I really like that you can just take the whole leg out with 3 bolts. This mechanism is quite elegant, I think. The 3 heavy servo motors are positioned in this servo hub. The rest of the parts are made out of just plastic carbon fiber tubes, so it's really lightweight. Oh shit, 340 grams only. Each servo motor weighs 70 grams times 3 motors, that's 210 grams. All the 3D printed parts, the carbon fiber tubes, weigh 140 grams. So 60% of this leg is just the motors and 40% is this mechanism, which I think is pretty good. I want the leg to be able to walk, therefore we need to make a step trajectory. So I'm thinking it's gonna start here, move in a straight line, and then do this top curve to get back to the starting position. So I want the curve to look like this. This is just a straight line, and this top curve we can just create by manually selecting a bunch of points. But you know what looks like a step curve? Cosine wave. So for the top curve, we're just gonna choose cosine wave from minus pi over 2 to pi over 2. And the cosine wave goes from 0 to 1 in the y-axis. To make the leg follow this path, we need to do something called interpolation. Here in this straight line, you might think you only need 2 points, but this is not the case. If you have point 1 and tell the leg to move to point 2, the movement in between these points is basically random because of the complex linkage. It doesn't move in a straight line, it's probably gonna look something like this. So to make the leg move in a straight line, what you need to do is create a bunch of points in between. That way you're giving the illusion that it moves in a straight line, although the movement in between the points is still random. So that's what we're gonna do for this line segment. We're gonna get a bunch of points, so it moves in a straight line. For the top curve, since we're gonna use cosine wave, we can just take these points on the x-axis and use a cosine function to get the y values. So we got our general shape of the leg path, but now we need to modify it, because I want to be able to control the step length and the step height. First we're going to create this line. I want it to be symmetric over the y-axis, so this is going to be 0, and it's going to go from minus step length over 2 to step length over 2. For example, if the step length is 200, this is going to go from minus 100 millimeters to 100 millimeters. Now we need to use these x values to get the cosine function. I want to choose the height of the step trajectory, so we're going to multiply the cosine wave by the step height. So it's just going to be the step height times cosine. Now we can't really feed these x values from the line to the cosine function directly, because the cosine function needs values from minus pi over 2 to pi over 2. So we need to map these x values to this range. And we're going to do that like this. So we take these x coordinates and we're going to divide them by the step length. That way we're going to get values from minus 1/2 to 1/2. And to get from this to minus pi over 2 to pi over 2, we're just going to multiply that by pi. And these are the values we're going to feed to the cosine function. When we add the line segment and the curve segment, we're going to get a lag path that looks like this. The length of this curve is step length, and the height of this curve is the step height. I chose, I think, 200 millimeters for the step length and 100 millimeters for the step height. Now, if we look at our lag, the origin is about here, and we want the lag path to be here. Therefore, we need to add some constant value to all of the y values of the curve, and we're going to move the curve down. Also, my lag uses a different coordinate system. I think this is x, but instead of y pointing up, we got z pointing down. So in the code, instead of y, I'm gonna use minus z. Okay, now we're gonna implement this in the code. So the true lag trajectory is gonna look something like this, and our goal is gonna be generating these points such that the lag follows this curve. So we get parameters like the step length and the step height. This is the step length, and this is the step height. Then we got step dx. This is just the spacing of the points, so dx is this. And I chose it to be 5 millimeters. We also got this ground height. So the ground height, what it does, it just moves this whole curve to the bottom. That way when you draw the lag, it's gonna be stepping at the bottom like it should. We're gonna start with the ground trajectory, which is the simpler one. Z is just gonna be ground height, it's not gonna change. And x is gonna start at step length over 2. So step length over 2, it's gonna be this point. And now I got this clock. I initialize it to be 0, and then I got this while cycle. Y is 0, z is just gonna be the ground height, and x is gonna actually iterate. So it's gonna start at step length over 2. We move the lag to that point, and we wait some delay, maybe 10 milliseconds. Then we add 1 to n, so now n is 1, and if we go through the cycle again, x is gonna be step length over 2 minus step dx times n. Step dx is 5 millimeters, n is 1, so this is gonna move 5 millimeters to the left, and we got our next point. Then we wait maybe 10 milliseconds again and get the next point. And this is gonna keep happening until we reach the end, where x is gonna be bigger than minus step length over 2. So minus step length over 2, that's here, and if x tries to get past that, it's gonna terminate this while cycle, and we're gonna move to this part of the code, which is the air trajectory. It's basically the same thing, but instead of moving from right to left, we move from left to right. So we start at minus step length over 2, and then instead of subtracting step dx times n, we add that. In the x-axis, we get the same coordinates, but in the y-axis, we use the cosine function. So we get cosine of x, but we can't really use this x because the cosine needs to get values from minus pi over 2 to pi over 2. So we need to map the x values to the correct range. We do this by dividing x by the step length. That way we get values from minus 1/2 to 1/2, and then we multiply it by pi. So we get values from minus pi over 2 to pi over 2. We feed this into the cosine and we get the correct trajectory. Then we also multiply it by the step height and at the ground height. That way the x values are going to be the same, and the y values is going to be the cosine wave, and the lag is going to move forward like this. So I just finished coding the step trajectory and it works pretty well. I was watching YouTube and I found this guy called Noé Ponto. To test the lag of his hexapod, he attached it to a skateboard and let it push around. I want to do the same thing. This guy printed some bars and used a string to attach it to the skateboard. I actually studied mechanical engineering, so I'm gonna use some duct tape.
Tak ráje. Sedni. Zůstaň. No. Zůstaň. No, zůstaň. No, šikovná. Zůstaň. No, počkej. Počkej, Ryan, pojď sem. Pojď sem. Však to je skateboard.
I hope you enjoyed this video. If you want to support me, you can do that on Patreon, and you will also get the files for this. Like, next video is probably gonna be on my master thesis, since I'm behind on that shit.